Hello and welcome to Database Design Chat number 18. Tonight, and it's tonight here, it might be morning where you're at. Tonight we're going to talk about concurrency. Now, this is the art of doing many, many things at the same time and making everybody believe you're doing a good job at it. And that's not exactly the truth, but we're going to talk about what concurrency in databases and how we want to control that as we're dealing with data. All right, so about me, I'm Lewis Davidson, DRSQL. I'm just the average person who does too many things at once, which kind of fits in nicely to concurrency. But so let's just talk about concurrency. What's the problem in concurrency? That is, you have resources and you need multiple people to be able to use those resources simultaneously and feel like they are both valued, and everything that every one of those persons does actually succeeds or fails and doesn't like vanish accidentally. And I always like to use the restroom example because there's multiple kinds of concurrency going on in the world, and that's one of the biggest places. If you have a sink, multiple people can use the sink at the same time. It's you don't have to keep people out of the sink, but you have those stalls in there that are used for many purposes. Those things are single use only, as far as I'm concerned. I'm just saying that's right. And so we have a lock on those doors, and we have a way to keep other people out while we're doing the things we have to do. All right. So restroom is a good kind of concurrency. Now, there's two kinds of concerns we're going to have when we're talking about concurrency. First is synchronous access. So let's say we have a resource in the database, we have a table, and we have two people that want to work with that table at the same time. Both of them want every single table to be available. How do we handle these things happening at the exact same time? Next is asynchronous access. And with asynchronous access, we're talking about processes believing that they have a copy of the data that they can operate on anytime they want to, and then push the data back. Now, what's interesting about this is that we're all dealing with both problems all the time because these operations can be milliseconds apart. You can think you updated a row and you were the only person that had the row. You updated the row. That's fine. But when you go, let's say you update a row, and if you don't know about locks, we'll talk about those some other day. But there's something that's holding you back. So if I'm updating table one and you're updating table one, and we're both updating the same row, one of us is going to have to wait till the other's finished. And that there is the problem. What do you do in that situation when you're finished updating? What happens to the next person's changes? Well, if they don't think about that, it overwrites. We'll look at that as examples in just a second. But the biggest concern here is that we don't like silent issues. I don't like problems that occur sometimes and only in extremely rare cases, because that extremely rare case is, it could be a big something. It could be someone's medicine. It could be a big transaction, but it could just be enough that it costs you hundreds and hundreds and thousands of dollars to hunt down why once every few weeks you lose a transaction. Those are the kinds of things that drive you nuts. It's not the things like, big errors. We find big errors. I can unit test for big errors, right? If someone's trying to store $1 million and the database only holds 10,000, I can test for that pretty easily. But how do I test for like Ticketmaster's problems, right? They have tens of millions of people all trying to get tickets to see Taylor Swift or whoever. How do they make sure that nobody gets the same seat, that everybody gets served? And I know there's lots of problems going on there. There's some of the problems that are kind of equity kind of problems. How do you make sure everybody gets a chance at the tickets properly, and how you limit the scalpers to the same amount of tickets as the rest of us, right? But the other problems are, how do you make sure that everybody gets that ticket 230, seat 1 and 2? I'm not going to see Taylor Swift. McCartney would be my last example of this personally, but how do you make sure that one seat doesn't get sold to 2 people? And then you have to, then the whole place sells out, and then you have to go, oh, I'm sorry, person X. It turns out that seat was sold twice. And so you've been randomly selected to not get that seat. That doesn't go over well. Oh, I know it's the chance of a lifetime, but sorry. We'll give you a seat at the next show. That helps. It doesn't help. All right. So the thing is, we have a row in the table that's misspelled, and we want to fix it. So we copy it out in user number 1. We make another copy, user number 2. And when I say copy, when you read a value, this is very typical. We all do this. When you pull stuff to the screen, you're making a copy of that data, right? You're not forcing the database to say, hold on to that copy. It's really hard to do. I mean, you can write something to the row that says, it's being now updated by user X. Hold on. Or, you can start a transaction, make a change in the row that exclusively locks it and dirties the page, and you can fetch the data. But that's really hard to do. Really not very optimal, because you don't want user 2 to have to wait. And depending on what kind of solution you have. I mean, if you're building a queue or a stack, sometimes those things sometimes is okay to skip over. It depends on what your need is. But okay, so we've got these 2 users and they made copies. Now they're preparing updates. So now user 1 has changed it to gray. User 2 is good. They spelled it differently. So now we have 2 sets of problems. What's the synchronous issue here? So when both of those users are making the changes to the row, what can happen? Well, there's a set of issues that are standardly discussed. And the first is phantom rows. And that's seeing a new row. So when I read the data out and I go back and I read the same data, I'll say select star from table where color equals gray, or what if that was the key, color equals gray, or row equals 1. Most of the time when you're doing kind of a simple edit, that's not going to be the case. We're not that phantom rows will largely come in when you're doing reporting or queries, like if you're doing medical something and you want to select from a person's medicine that they're being received, and you want to make sure that nobody else can create new rows in the output. So phantom rows, non-repeatable reads, the hardest term to get in, because it's kind of backwards. But if when I read that data, in this case, the gray, and I pulled it back and I want to make the update, I want to make sure that row is still there and it looks exactly like I asked it to. So if it's changed, it's a non-repeatable read. A dirty read. If user 2 there is making a change to the row and they haven't committed their change, they haven't said, I'm done with this row, and I've done the update, but I'm not sure that it's right. Let me check it first. And somebody else can read it. That's considered a dirty read. So you don't want someone going back and looking at data that hasn't been finalized for the user. And then there's expired or older data. So in this case, you might say, I have a copy of the data. You have a copy of the data. When you've made a change to the data, my data is expired. It's no longer the real data. So I need to refresh it before I start making changes. So let's look at this. So in a lot of cases, user 1 goes in, makes the edit, and User 2 has to wait. Well, that's fine. So user 2 says, I'm done. I've updated to gray. And then they think it's over. That user 1 thinks it's done. Now user 2, they get finished with their edit. They updated to gray, GREY. Now we have a different set of issues. This is probably not so simple of a thing that they're actually just editing the same value to something else. This may be they've got the whole screen up, and there's 20 columns in this table. Each one are updating different columns. And so this one updates the name, this one updates the phone number. But they have copies of the whole data, so they update all the values. And they don't change. So we have this like different problem. And so this is the asynchronous problem I'm talking about. This may be cached, this may be like immediate. This wait may be a day, like they've held the data for a day. So we have to think about this as asynchronous problems now. So in the asynchronous flow, 2 users fetch some data. 1 user updates the data. The second user updates data based on their expectations or reads it and holds it. It's that problem we just showed that's caused by the asynchronous problem. Okay. So there's a few ways we handle this. One is chaos. The last user, the last writer wins. That was the thing we showed the first time. The second more likely thing that you should do is that you check these cache rows to see if the data has changed. So there in SQL Server, there's a timestamp column, which is really a row version column. They're never going to change the name, but you maybe write that value using a row last modified time controlled by a trigger. Never trust the front end to always do what it's expected to do. Not because developer 1 isn't good or developer 2 or division 1, but there's always just that possibility that someone misses writing the row and missing saying, hey, I've changed this row. They may have changed some data in there, but they didn't change the change tracking thing. So if you're gonna have a column that says I was updated at this time, make sure it's controlled automatically. Or in some cases, you just check all of the data. We do that a lot in the data warehousing sort of scenario, but it's because usually you're trying to keep the columns pretty lean. It's not typically good to do in some OLTP kind of client operations because you might have a text column in there, varchar max, but textual data, a lot of textual data, and that can be really hard to pull down because sometimes it can be a gigabyte, right? And you don't want to pull down a gigabyte, check and see if it matches just to say, no, I can't update it. So those are the things. Or let's be realistic. Sometimes it's a little bit of both. So what if you can update thousands of rows? Can you check the timestamps? Are you going to cache all of that? The answer typically is no. Ideally, you're going to use a more pessimistic lock, which is to say, I'm going to lock all the rows somehow. I'm going to make my change, and then I'm going to update it. And we're going to assume, and in that process, we're going to update that optimistic locking mechanism, and we're going to assume all other users have to follow that. And that's like if you're updating that's adding a column or something like that. It's a little bit harder to do. All right, so what happens is now we have the 2 copies, they've made their changes, they're going to lay in their edits. This user waits. And then the next user comes in and they modify it. Well, when they check, they get back a message somehow that it's changed. This row is not the row you started with. And so then you can do what you want to do, fetch the gray, compare what you want to do with it. But no inadvertent data loss occurs. I'm not even going to change that. And like I said, just in all cases, we want to make sure that we're doing what we need to do. Maybe you want to update it to GREY. Maybe GREY is fine. But as long as your customer knows that, then this process is not lossy. And we don't want to lose data in any process, right? So we'll talk deeper about the mechanisms that are used. Sometimes waiting actually just means returning a message and saying, no, you can't do that. Try again. When you're doing something like a multi-value concurrency control. And then different databases use that. SQL Server uses it for memory optimized tables. But if you have one user updating one piece of data or reading one piece of data, it's completely easy. And this concurrency actually is going to expand to reading, because if I read in a bunch of data, I have some expectations on that. I need to make sure I don't get non-repeatable reads or phantom rows. That's all part of the process. So updating is one thing, reading is another. And again, if you have some specific need to make sure you get the exact right answer, like again, I go back to medicines, I go to things that matter, then it's really important to make sure. Like you don't want them to put in some medicine and then talking about dirty reads, and you're reading that and you see that they put in the medicine, and then they roll it back and you don't do it. Now, keep in mind, all of this can be overridden by delete. I mean, someone can go in and delete the data later and it not turn out to be there. So this is more than just a concurrency problem, but it's certainly a problem that needs to be handled and understood what might happen concurrently, and then test. We'll talk even more about how do you test that in the future as well. So multiple users just reading, or multiple users working on two different tables. Like if you have 1,000 users and 1,000 tables and all writing and reading to the same table, it's still just kind of a single threaded operation. But the OS, the database management system, that's then multi-threaded. But we don't have to worry about the multi-threaded in the one piece of data. But if everybody's trying to update the same row in the table, things get complicated. You just have to make sure you understand how it works. The people who build the RDBMSs have to make sure how it works. They don't just, they could just say everybody who's using a table locks it. Right? But that's not good. That doesn't provide the performance we so desire. And we never want to lose any data. Like that's number one. I know there's databases that have this eventually consistent stuff, and that is cool for certain kinds of things. If I'm building a forum post and it happens that I lose a forum post because of two users modifying, okay, that happens. I'll fix it. But again, medicine, transactions, anything like that. Somebody buys something, somebody going to Amazon, put in an order, and it just goes away because of some concurrency problem. All right, so that's at a high level what concurrency is, and some things to think about when you're building it. Again, I'm going to harp on this again. It's been so long since I've done these things, and this is my second one after I've come back. Both of them I mentioned correctness. Pretty much everyone before this and after this will mention that. Concurrency is the biggest silent killer of data integrity. That's why when we're talking about it, when you're building a table, when you're building indexes, when you're building the whole thing, you got to think about concurrency. As we start designing tables, thinking about concurrency and thinking about how it might happen. And as I mentioned testing, it's really hard to test what happens when you have multiple people doing things at the same time. When we start coding this, I'll show you some techniques for how you slow down time by different kinds of operations, transactions, making them hold in time instead of go away really fast. Because a lot of these transactions you'll do even in production with thousands of users, they take milliseconds. But if two people are doing things in the same millisecond, which is more likely when you have more users, it's really hard to simulate. I've got some test rigs which I use to simulate such things, and you can force concurrency issues to happen. It's just not something you typically can unit test in the same sort of way that you test other things. And I already covered that. So and it's not just the database management system's job. It's partially their job to make sure that if two rows are being updated at the same time, they don't get stomped on. But it's your job to say what happens afterwards. Every synchronous data issue where two people are modifying the same resource at the same time, if you're not careful, every synchronous problem becomes an asynchronous problem. Well, I'm back, and I have to say, I'm still taking too long. This is 25 minutes on my clock. I think it's a little bit less. I'll cut a little out, but there's a lot to say about concurrency. And this is, I decided when I was building these chats, I was going to make it the director's cut of my database design sessions. And this is the case. Concurrency is big. It's one of the things that's so important that you have to understand. And I hope this helped. I'll see you next time. Bye-bye.